Hello and welcome to my channel. This video is an assignment sent in by a subscriber on how to use the CES production function to calculate the optimal input and the maximum output. The challenge says an industry has a generalized CES production function Q equal A alpha K raised to the power of minus P plus 1 minus alpha times L raised to the power of minus P close brackets raised to the power of minus 1 over P, where A equal 100, alpha equal 0.2, P equal minus 0.5. If the industry's budget function is given as 12K plus 6L equal 9,000, determine A, the optimal input, B, the maximum output. CES implements casting elasticity of substitution. In the given equation, we have A means level of technology. The alpha there means share of capital in total output. K, capital input. L means labor input. P is the elasticity of substitution between labor and capital. First of all, we're going to reduce the industry's budget function to the barest minimum by dividing through by 6. 12K divided by 6, 2K plus 6L divided by 6, L because 6 divides 6 gives 1, so we have 1L here. 9,000 divided by 6 gives this value. So we'll be working with this as the industry's budget function instead of this. Now we'll rewrite the production function by substituting all these values given into the equation. Q equal A, the value of A given is 100, our alpha given is 0.2, K raised to the power of minus P, of course the P value given is minus 0.5, plus 1 minus alpha, close bracket, times L raised to the power of minus P. We close our bracket, raised to the power of minus 1 over P. We have 100, we have our open square bracket, 0.2K minus times minus gives plus, so we have raised to the power of positive 0.5 here, plus 1 minus 0.2 gives 0.8, L, of course, minus times minus again we have plus, so we have raised to the power of 0.5, close square bracket, minus 1 divided by minus 0.5 gives 2, right? So work with this formula to get the partial derivative of K and L. The next step is to find the partial derivative of Q with respect to K and L. So we represent the partial derivative of Q with respect to K as MPK. So we start by multiplying 2 by 100. So writing down all these values here. Differentiating 0.2K, 0.5 times 0.2K gives 0.1K. 0.5 here minus 1 gives minus 0.5. Let's also proceed to finding the partial derivative of Q with respect to L. We represent that with MPL. So we start 2 times 100. Then write down all these values here. Differentiating 0.8L here, we have 0.5 times 0.8 gives 0.4L. 0.5 minus 1 minus 0.5. Looking at MPK and MPL, we could see that this and this are equal, so they both cancel out. When this happens, for MPK, we are left with 0.1K raised to the power of minus 0.5. Going back to the budget function given, the coefficient of K here is 2, so we'll divide this by 2. Equating this with the MPL value, of course, when this cancelled out for MPL, we got dividing this by the coefficient of L in our budget function. The coefficient of L here is 1. Next step is to cross multiply. 0.1K raised to the power of minus 0.5 times 1 gives this value here equal 0.4L raised to the power of minus times 2 gives this value here. Next step is to divide both sides by 0.1. When that happens, 0.1 here will cancel 0.1 here and we'll be left with, right, 0.8L raised to the power of minus 0.5 divided by 0.1 gives, bringing this in the form of fraction we have. This minus here represents 1 over, when the K here raised to the power of minus 0.5 goes down, it becomes K raised to the power of 0.5. Same goes with this. We have 8 here over, bringing L raised to the power of minus 0.5 down becomes L raised to the power of 0.5. Now we'll cross multiply here. L raised to the power of 0.5 times 1 gives this value. 8 times k raised to the power of 0.5 gives this value here. Take the square of both sides. L raised to the power of 0.5 times 2. Of course, 0.5 times 2 gives 1. L is 1 equal 8 square, 64. K raised to the power of 0.5 times 2 gives k. Finally, we have L equal 64k. But our budget function equation given is this. Now we'll substitute the value we got for L into the equation. Now the equation changes to 2k plus. In place of L, we'll write 64k because 64k is the value of L equal 1,500. 2k plus 64k. 66k equal 1,500. K value will be 1,500 divided by 66. Gives 22.7, which is approximately 23 units. Remember, we got value for the labor input to be 64k. Since we now have value for k, which is 23 units, we'll substitute 23 into the equation here. Our labor value will be 64 times k. K value we got 23, which is 1472 units. So we succeeded in answering the A part of the question, which said determine the minimal input. Remember, we did say k is the capital input and L is the labor input. Now let's proceed to the B part of the question. Determine the maximum output. Q equal 100 square bracket here 0.2 times k. The k value we got 23 here raised to the power of 0.5 plus 0.8 L. Our L we got this value here raised to the power of 0.5 close square bracket, then raised to the power of 2. Going forward, Q equal 100 times 0.2 times 23 raised to the power of 0.5, 4.79 plus 0.8 times 1472 raised to the power of 0.5 gives 38.37 all square. 100, 0.2 times 4.79 gives this value here plus 0.8 times this value gives 30.693. Of course, close our square bracket all square. Going forward, 100, this value plus this value gives this value here all square. 100, the square of this gives this value here. 100 times this gives this value here. So this is the value of the maximum output. We've succeeded in answering all the questions. I hope this video helps. Please do well to like this video, leave a comment, share, and subscribe to my channel. Thanks so much for watching. Bye.